I grabbed a few relays off the shelf just to basically explain this, just so some people can get a better understanding. A lot of people may not realize it. Some relays have schematics on it, some don't. But just for an example, this little square box right here, that's your diode. Right here, that's a diode connected, and also over here, this little square box, that's a diode as well. For the most part, these are just a larger external diode. These are your internal diodes already inside this diode, inside the relay, designed to protect the circuit. If we was to pop this cover off, you'll probably see a little diode connected right across this circuit right here. So basically, it's extremely important how you would connect these diodes. Even though we can't visibly see it and there's no marking on this stating that it's a diode, your cathode itself would be connected to 86. So 86 in this relay, this is your positive side that would activate this relay. 85 is your ground. So this is just a standard Volkswagen Audi relay. And this is wired in a way for reverse bias. So for example, positive voltage is going here and your cathode is here, and that blocks the flow of any type of voltage shooting across if you was to have this relay switched around backwards. So here, if this is your silver stripe right here, so a lot of times I would think of this as a wall or something that's blocking. That way, this is your reverse bias right here. If you was to connect positive here, this would be forward bias. This would allow voltage to travel here, but be blocked from coming here. You don't want that. That's going to short out your contacts. If this was hooked up backwards, meaning the cathode was over here and the anode was over this side, you're going to create a direct short to ground and it's going to burn up this relay. But the reason they have these hooked up this way, your cathode on your positive. So remember, this blocks the flow of voltage right here. That prevents, this is wired in a reverse bias way. This prevents the kickback voltage when this relay coil collapses. And something small as this. And you can only imagine if you're controlling a heavy duty starter relay, starter solenoid, anything heavy duty or like a solenoid like this, you want to definitely make sure you have your protection in here just to prevent any type of kickback, or most commonly called flyback. Your flyback voltage or a flyback diode from destroying your coil itself. This actually protects the contacts in these little relays. If this relay did not have a diode in it, every time this relay is energized, it'll create an arc inside and eventually burn up the contacts. And a lot of heavy duty contactors, and I probably have something on the shelf that we probably tossed out, where you can see contacts were just destroyed because of relays being constantly energized. And if you don't have anything to protect those contacts, there's going to be a lot of arcing and carbon buildup on that. So that prevents a lot of that and increases the longevity of this. Therefore, these solid state relays do not have any type of flyback protection, and that hence the critical point of making sure you have something good like this. And it don't have to be expensive like this. You can buy something cheaper, but make sure you do your research and have a good high quality diode to prevent. I'll spend $7 or $20 on a diode just to prevent from damaging anything in that Motec circuit or damaging the fuel pumps or anything like that. Spend a little extra money, and if it can protect, in the long run, that's what we're going to do. Sometimes you may have to shortcut it, and you got to be careful in certain areas, but certain areas you don't want to take any shortcuts in. All right, let's go to the next step. But I wanted to give basically some type of explanation of the importance on if you decide to take that type of route, on how to set your stuff up and do the research before you make any type of connections. But pretty much, if given the time, I'm going to have the stuff hooked up in the Audi TT anyway, and I'll probably do a short little video and use my signal generator, and we'll generate a square wave frequency and adjust the duty cycle before we even connect it to the Motec. Play with the duty cycle, use a solid state relay and with the flyback diode and everything connected, and play with the fuel pump and play with the duty cycle and ramp up the speed of the fuel pump, slow the speed down, and then take a look at the fuel pressure gauge also and see what type of effects that is having on the gauge running, because I'm kind of curious about that also to see how it's going to operate, as well as the fact that we're using a mechanical style fuel pressure regulator. This would be our electric style for our direct injection pump, and of course the aeromotive one that we have on Teddy's car is the mechanical one. So we'll get an opportunity to play with that. Next thing I wanted to go into a little bit was, this also, since we're talking about relays, one of the very popular relays that's on the market. And I'll say this with caution. These are awesome. Do not get me wrong, but this is a whole nother league. This is industrial longevity, long term. This is for short spurts. If you're running down a quarter-mile racetrack and you're activating your nitrous solenoid, or you're just running in a short sprint and you hit nitrous for about 10, 15, 20 seconds, that's fine. Something like this is what you want to go with. It's a lot cheaper than these solid state relays over here, and this will work excellent, as I stated. But this would be, I would say, in short runs. If you're talking about longevity and something that's going to be running for 8 hours, 10 hours, 24 hours, around the clock, this is your best bet right here. Like I said before, I've seen these things operate for, honestly, even 48, 72 hours straight without us even shutting down any conveyor equipment, moving products out the building, trying to get stuff out the system, out the door, and don't even shut down. We just mandatory overtime, and people are running and working around the clock, and the machines are steadily running, and these bad boys are just, they're kicking ass. I'm just keeping it real. They're kicking ass and lasting a long time. Something like this, it'll burn up, honestly, within, I would say, with the applications that we use them in, this would last maybe 2 minutes, 3 minutes, this years, but this wasn't designed for lasting 5, 20, 30 minutes, I'll say, or maybe an hour under continuous duty, because you have a plastic housing also, so it's nothing in here really designed to dissipate a lot of the heat also. So that's why I said this is an excellent product. I love it. As I stated before, I was going to pick up a few of these myself, and if we're going to use it for short bursts of runs, but I decided in most cases we're going to pop this in Teddy's car. He's going to be in Vegas for the most part. I'm in a different state. And I don't want to fly out to Vegas just to swap out a relay. And I know Teddy could do it himself, so I would just say, hey, bro, FaceTime me, and I talk him through it, and make sure we got all the connections right, and we'll run some tests and stuff like that if we have to. But either way, for the most part, I want to put some durable, reliable parts on this car. A lot of the stuff that we can handle at for the most part, and then if Teddy want to upgrade to something even better, so be it. But just for getting everything kicked off and everything, this will be fine. Now that I can finally get back over to this. Finally, we have the wiring connections for our solenoid valve, and this is the valve that goes into our direct injection pump. Now, there's a few things I may change. I was deciding maybe I will still use the sensor to monitor the cam load, but either way, I already have a PID map inside the system where I can use the low pressure sensor to monitor the incoming, which is here, our low pressure fill system sensor to monitor incoming fill pressure. We have our high pressure sensor. This goes into our fill rail. I would pretty much use this sensor to regulate the duty cycle on this. Set this up into the Motec. This will maintain our rail pressure. This is actually maintaining the rail pressure. All this is just going to be the input going to the Motec that pretty much says, hey, I want to maintain 800 PSI of rail pressure, or I want to maintain 1500 or 2000 PSI of rail pressure. So therefore, we're going to adjust the duty cycle on this for whatever RPM we're at to modulate the duty cycle. So for example, at idle, we're probably going to be running anywhere from 800 to 1000 PSI fill pressure on our direct injection side. Over here, a lot lower. We're only going to be running maybe I will possibly have a static pressure of 50 psi. So for example, if we're running 50 psi and our boost pressure is 1-to-1, with a static pressure of 50 psi and a boost pressure, for example, of 40 psi, right off the bat, once at full boost, we'll be running 90 psi of fill pressure system pressure on the other side, not the direct injection side, but on the port side, or pretty much that's really feeding both. So it's going to be a little bit tricky with the tuning, because as the 1-to-1 increases, of course, that's going to also play a role with the system rail pressure increasing a little bit also. That's pretty much feeding the direct injection pump. But once we get all this stuff together, we'll get a chance to play with it. That's going to be the fun part, with the fun, tedious, and probably losing hair moments of making sure we get all of this stuff configured right. But once we get it right, I know it's going to be fun and it's going to be nice, because then the sky is the limit. Then we can start playing around with some nice stuff right off the bat. One of the last sensors that I have not connected yet is our flex fill sensor.
YouTube video out now, man. Like, comment, subscribe.